Okay, so last time we talked about the half adder, um and then in this video let's talk about the full adder. So just to recall what the half adder did, um so the half adder was a circuit we designed that allowed us to add two bits together and then tell us what they sum to and then the carry for the next uh operation. So if we have 1 1, right, the sum is 0 and the carry is going to be 1. So half adder let us know, okay, half adder gave two outputs, the sum and the carry. But what the full adder, this is half adder, but then what the full adder is going to allow us to do um, is, so let's say we have our 2 bits again, but then we have, so this is going to be our CI. What the full adder is going to allow us to do um, is to add 3 bits together. So for example, right, if we have like these other operations here, and then this carry, like we have previous calculations, and we have a carry of 1 over here, and we add this to these 2 bits right here. How do we add these 3 bits together now? So I'll erase this actually. So if this is your CI, like your carry bit, how do we add these together, right? Your sum, and then give us our new carry. Yeah, so you're just adding one more step to it. You're just adding 3 bits together. And the circuit to do this is called the full adder. Okay, so how do we do this? So I kind of want to do like a top-down approach here. So like first, we'll just start with, I claim that this is the circuit to do full adder, and we'll verify this is the case. And so here where I put H, that's half adder, this is an OR, and then these are all of our inputs. So, and then also we did this last time, right? Where I did A and B because I don't want to use X and Y over here, but when we write sum and carry, this is what we mean. And then the output for this, sum F is your final sum, and then the CI plus 1 is your next carry bit. So how do we do this? Okay, so let's just go ahead and get started. So we write, let's just first do sum F. So we say this is equal to the two inputs here are sum 1 and CI, right? So we can say, first let's write sum F is equal to this. So A naught B plus A B naught, where A is equal to sum 1 and B is equal to CI. Okay, and then what is sum 1? Sum 1 is, we have to unpack it more with this definition. So it's going to be X naught Y plus X Y naught. And then now we're ready to go. So now we can go ahead and compute this over here. So we're going to negate A, and then times CI, and then plus just normal A, times the negation of this. And now here we want to repeatedly use De Morgan's law to unpack this. So this is going to be and then further, this is going to become X plus Y bar times, and then X bar plus Y. And then if we multiply this out, right, we get X bar plus x y plus x bar y bar plus y bar y. And now we use the Boolean identity here that a Boolean variable times its negation is always going to be 0. So these are going to go away. And then now we have xy plus x bar y bar times ci. So this is going to be xy ci plus x bar y bar ci. So this right here is this, and then we're gonna fold this out over here. So plus x bar y ci bar plus x y bar ci bar. So this is the output of sum f. So this is gonna be sum f, and then we want to find what the output of ci plus 1 is. So for ci plus 1, this is going to be our a and b are carry 1 and carry 2. So this is going to be carry 1 times carry 2, and then carry 1 is just x times y, and then carry 2 is going to be sum 1 times ci. So it's going to be, this is sum 1, right? So it's going to be x y yeah, let me just do it completely. So and then yeah, so it's ci times someone. So x bar y ci plus like that. Okay. Sorry, this is gonna be a plus because this is an OR operation. It's gonna be plus. Yeah, I was like, this looks weird. Okay, and now we can just leave this as is. So I'll just take away the parentheses. Okay. So now this is the output of our full adder. Now, how do we know that this is correct? This is actually going to add our 2 bits together properly. Just to give myself space, I'm going to rewrite this up here. So plus x. Hopefully I'm copying this down, right? Yeah, this looks fine. So we're going to erase this. And then, okay, I guess this is fine actually. Okay, so now, last time when we did the half adder, we built this table for it, and then we used sum of product expansion to create a Boolean function for it. So we're going to do the same thing for this. So here, where our 3 inputs are x, y, and ci, and our outputs are going to be sum and then carry, right? And so since we have 3 independent variables with 2 inputs each, we're going to have a total of 8 rows. So, right, these are just all, okay. So yeah, it should be 8. And then we're also going to fill in this, so, okay. And now we're going to compute, we're just going to think about what these have to be. So this is going to be 1 plus 1 is 0, carry 1, this is going to be 1, 0. And this should be, you can kind of like do this also in your head. So 1 carry 0, 0 carry 0. 0 carry 1, 1 carry 0. Now 1 plus 1 plus 1 is going to be 1 and then carry 1. This one was like this trickiest one probably. And then 0 carry 1. Okay. And now we want to use our sum of product expansions to find out what SF is here. So we're just going to look at all where we have 1s, right? Just like last time. So this one, this one, this one, and this one. And then we get that SF is equal to X Y bar CI bar plus X bar Y bar CI plus, we're gonna keep going down, X bar Y CI bar plus XY CI. And now if I did this right, this should match exactly this, right? So we have XY CI X bar, this one, and then and then these guys. So what we're showing here is that our theoretical like what we know should be the case for our outputs matches what we have here. So at least for our going from theory to implementation, the sum is fine. And then now for CI plus 1, it's going to be this one, this one, this one, and this one. And then so now if we do the expansion again, this is going to be X Y bar CI plus X bar Y CI plus XY CI plus XY CI bar. And now what we can notice here is that I'm just going to put this all in one line. Plus X bar Y CI plus XY CI plus, right? These might not look equivalent just yet. But what we can see here is that these share a common factor of XY. So coming over here, this is like XY CI plus CI bar. And now this is another Boolean identity, which you can verify by just plugging in all combinations of or really you can just do like we can just show that like if CI is 1, then 1 plus 1 not equals 0, or if CI is 0, then 0 plus, this is always going to be 0. This is a Boolean identity. So sorry, no. It's always going to be 1. Right, so this is always going to be 1, so this becomes XY. And then so now we have equals X Y bar CI plus X bar Y CI plus XY. And now this is equivalent to this up here. So we show that the theory what we expect it to be matches the actual implementation. So this is more like a top down way of thinking about it as opposed to like a bottom up. So we can see that like all the full adder is doing is adding a third bit, and the circuit becomes much more complicated. And so what we're building up to is we want to be able to implement as many full adders as we need in conjunction in order to add actual integers together. So we want to figure out a way to implement these full adders which are dealing with binary numbers, and we want to apply this to adding integers together so that our calculator works, because we don't want to deal with having to add and deal with binary numbers all the time. We want to allow like ourselves to enter in integers, add them together, and then have the implementation under the hood be these full adders, these circuits. Yeah. Okay.